we're going to do now is start with the baseline runner and see if we can optimize this using automatic optimization in Turbine 1 in order to remove the possibility of cavitation and improve its efficiency in the process. And here is the workflow used by the optimization, where the blade loading and stacking parameters are used to generate the blade shape in Turbine 1, and then the resulting performance parameters are fed into the optimizer, which basically applies MOGA to drive the solution towards the optimum design. And of course, we need to start by specifying the range of variation for the input parameters, which are the stream-wise loading parameters and also the wrap angle or stacking at the leading edge, because it also has an influence on the surface pressure distribution. And whereas by default the ranges are set to plus minus 10% of the baseline values for each parameter, as you can see here, but there is a machine learning based feature in Turbine 1 that can provide initial range estimates for these stream-wise loading parameters as well as the wrap angle. And this is because we want to explore a large design space, but also try and avoid infeasible solutions. And then these are the constraints that were used. So we constrained the throw to plus minus 5% to maintain the flow rate and so effectively the turbine power. And then the secondary flow factor is also limited to avoid very high values to plus minus 10%. And finally, for the optimization objectives, we want to minimize the total profile loss to increase the runner efficiency, and at the same time we want to maximize the minimum pressure in order to remove the cavitation scenario we saw earlier. And so once the optimization run is complete, which is very fast and only takes about an hour or so on a single core machine, we can see all the designs on a scatter plot between the two objectives, the profile loss on the x-axis and the blade minimum pressure on the y-axis, like that. And the target case, which is the baseline runner, actually sits here with quite a low minimum pressure and high profile loss. Next, we can choose to see only the feasible designs which respect all of our specified constraints. And then we can also choose to see the Pareto front of the optimum designs, from which we can pick and analyze any design of interest. And in this case, we select a design from the middle of the Pareto front, which provides a good trade-off between the profile loss or the efficiency and the minimum pressure or cavitation. And so we use this design for further analysis and for comparison with the baseline runner. And in fact, this is what changed as a result of the optimization. So for the stream-wise blade loading, you can see that compared to the baseline runner, the optimizer has tried to make the shroud more aft-loaded in order to reduce the profile loss. And as a result, the optimized runner is actually looking very different from the baseline, as shown here. And what you can also see here is, while the baseline runner had zero stacking at the leading edge, the optimizer has resulted in a forward stacking of 8 degrees. And then due to this combination of aft loading at the shroud and this forward stacking, the surface pressure jump is reduced in the front portion of the runner compared to the baseline, which eventually results in a positive pressure throughout this area, just basically eliminating the risk of cavitation in this region. And then here are the results for the optimized runner, and it's interesting to see the effect on the Turbine 1 performance parameters, where there is a significant reduction in the total profile loss as a result of the optimization, with only a slight change in the throat area. And when we actually run CFD on the new runner, what we find is about 1 percentage point improvement in the total to total and the total to static efficiencies for both the runner and the stage, and also a corresponding increase in the turbine power output. And if we look at this CFD pressure distribution, then it is confirmed that, just as the inverse design had predicted, the surface pressure is staying above the vapor pressure throughout the suction surface, eliminating any chances of cavitation in the runner.